So, you ever wonder what's really happening inside those massive data centers that power tools like ChatGPT? Well, it's definitely not magic. It's all about specialized hardware. Today, we're going to pull back the curtain and look at the silicon brains that are making this whole AI revolution possible.
All right, so here's the game plan. We're going to trace the story of how AI basically outgrew our traditional computers. We'll kick things off with the huge processing problem they ran into, then we'll discover the accidental hero that popped up from the world of gaming, and finally, see how all of that led to the custom-built chips that unlocked the AI we're all using today.
Okay, so to really get why we need these crazy special chips, we have to first understand why our normal everyday computer processors just hit a wall. What was this fundamental problem that AI created?
It really boils down to two completely different ways of thinking about work. A traditional CPU, the processor in your laptop, is like a single brilliant master chef. They are incredibly fast and precise at handling one complex dish at a time. But modern AI, it's not about one complex dish. It's more like needing to chop 1,000 onions all at the exact same time. That master chef, for all their incredible skill, is going to be a massive bottleneck.
This whole process, as IBM defines it, is all about analyzing these huge, constantly changing data sets. And when you try to tackle that with a processor that works sequentially, one step at a time, like a CPU, well, you create what they call frustrating bottlenecks. That one-by-one approach just can't keep up. And the kinds of jobs that define modern AI, we're talking neural networks, deep learning, they're all about spotting patterns in unbelievable amounts of data. And to do that, they have to perform millions, heck, billions of simple calculations all at once. A CPU just isn't built for that kind of parallel chaos. A totally new game plan was needed.
And that new approach, the solution to this huge bottleneck, it came from a place nobody really expected: computer graphics and video games. And enter the GPU, the graphics processing unit. So instead of having just a few genius-level cores like a CPU, a GPU has an army of thousands of simpler cores. Its original job was to render every single pixel on your screen for video games, a task that, you guessed it, requires doing thousands of small jobs all at once. And that's when researchers had this aha moment. This architecture was perfect for that thousand-onion problem of AI.
I mean, just look at this chart. It lays out the difference perfectly. A CPU has just a handful of really powerful cores. A GPU, on the other hand, is all about brute force in numbers. That huge army of cores, originally designed just to make your games look pretty, turned out to be the accidental key to unlocking the power needed to train modern AI. So how in the world do you coordinate an army of thousands of little processors without it just turning into complete chaos? Well, it turns out there's a surprisingly clever command structure. It's managed by a system like NVIDIA's CUDA. And honestly, the best way to think about it is like a military hierarchy. You've got your individual soldiers, those are the threads, doing the basic calculations. They're grouped into small squads of 32 called warps. Those squads form larger platoons, or blocks, and the entire army of blocks working on the problem, that's called the grid. It's a brilliant system for turning pure chaos into coordinated power. And this structure is exactly what makes GPUs so scalable. You can just keep adding more and more blocks, more platoons, to the army to tackle bigger and bigger problems. It's how a single piece of hardware can break down a monstrously huge AI task into millions of little, manageable pieces. But here's the thing. While GPUs were this amazing accidental solution, they were still generalists, right? They had to be good at gaming and AI. And that flexibility wasn't always the most efficient, which led to the next logical step: building a specialist. And it all kicked off with this one simple question. What if you just stripped away everything that wasn't absolutely essential for machine learning? What if you built a chip from the ground up to do one thing and one thing only? And the answer was Google's Tensor Processing Unit, or TPU. It's an ASIC, that stands for Application-Specific Integrated Circuit, and that name says it all. It's not a generalist like a GPU, it's a specialist, custom-built to do one thing with just mind-boggling efficiency: the core math of AI, which involves these giant arrays of numbers called tensors. So its architecture is lean, mean, and stripped down for pure performance. At its very heart is the matrix multiplication unit, the MXU, an engine built for one job. It's got super fast memory right there on the chip to avoid any slowdowns. Basically, anything not essential for the raw mathematics of neural networks is just gone.
So how does it get this incredible speed? Well, the secret sauce is something called a systolic array. The best way to picture it is like a hardware conveyor belt for data. Numbers just flow through this grid of simple processors, getting multiplied and added in this perfectly synchronized rhythm. This pipeline design makes the matrix math at the core of AI just ridiculously fast.
So this brings us to the most important part of the whole story. This isn't just about cool computer chips. This evolution in hardware is directly responsible for the AI software that is literally changing our world. These chips didn't just speed things up, they made entirely new kinds of AI even possible.
Okay, let's take large language models, LLMs, the tech behind ChatGPT. Their incredible power comes from a software architecture called the transformer model. And this model has a very, very specific requirement that makes it a perfect soulmate for this new kind of hardware.
And this is the absolute key. Older AI models, they would read a sentence one word at a time, sequentially. But the transformer's big breakthrough, this thing called self-attention, is totally different. It looks at every single word in a sentence in relation to every other word, all at the exact same time. Understanding that complete context is a massively parallel job, one that would be basically impossible on a traditional CPU.
And right there, that's the perfect summary of the AI revolution. It's a feedback loop. The parallel power of GPUs and TPUs made the transformer model a reality. And in turn, the incredible success of transformers created this insatiable demand for even more powerful parallel hardware. Hardware and software didn't just evolve side by side, they literally pulled each other forward. So this leaves us with one last big thought to ponder. As AI models get even bigger, even more complex, the hardware that runs them is going to have to evolve again. The chips that enabled today's revolution might just be the bottlenecks of tomorrow, which begs the question, what kind of hardware will the next breakthrough require?